Everybody. In the last lecture, we were describing about the stability, and we described what is the stability in general, what is the meaning of voltage stability, what is the meaning of angle stability. While describing the voltage stability, we told it is the ability of the system. It is the ability of the system. When we call it is a system, it is a power system. So it is the ability of the system to retain the voltages of all the buses in a specific range. So following some disturbance, even if some disturbance comes, disturbance may be in terms of active power, it may be in terms of reactive power, and we know because of the increase of load, voltage goes down, and it's the responsibility of the power engineer to maintain the voltage of all the buses within its range. So the system should be capable of doing that, and we have seen that it is because of the mainly the angle stability is related with the active power, and voltage stability is mainly related with the reactive power. If our system is not able to supply the reactive power demanded, then voltage goes down. Or you can say voltage instability arises due to the inability of the system to meet the reactive power demand. So if it is not able to meet the reactive power demand, voltage of some of the buses near to the load buses, first of all near to the load buses, try to go down. Then after some time in a certain area, the voltage goes down, then the profile of the voltage in the certain area become low. When the voltage profile become low, then it is not allowed. Sometime it happens. You see, as I told that active power it mainly affects the frequency, but I am not saying it is completely or solely affecting the frequency. It also affects the voltage of the system. Similarly, as I told, the reactive power mainly affects the voltage, but I am not saying it is the solely affecting the voltage. It also affects the frequency. But although the dependency is less, so when the load changes, it affects both voltage and frequency, voltage or power angle. It is affected, both are affected, but main effect on voltage is because of the reactive power. And when the system is not able to, and you know who is supplying demand, demand is the load. Demand comes from the load. It may be reactive power demand, it may be active power demand, and any power may be more than the supplied. But who supply the reactive power? Reactive power is being supplied or reactive power is being controlled through the excitation, as well as it is supplied by the, yes, do you know what are the other than the excitation, from where the reactive power comes? यस तनु बता सकते हैं? एक्साइटेशन सिस्टम आपने पढ़ा हुआ है, एंड अदर देन द एक्साइटेशन फ्रॉम देयर द रिएक्टिव पावर कम्स. हेलो, आर यू लिसनिंग मी?
यस सर.
हाँ, बताओ, व्हाट आर द सोर्सेस ऑफ रिएक्टिव पावर? रिएक्टिव पावर कहाँ से आता है? तनु बताओ.
सर एक्साइटेशन पे डिपेंड करेगा सर.
इसमें एक्साइटेशन तो बता दिया मैंने. अदर देन एक्साइटेशन, व्हाट आर द सोर्सेस ऑफ द रिएक्टिव पावर? Transmission lines are also the sources of the reactive power. You know, there is a capacitance between the overhead transmission line and earth. There is a capacitor. So the reactive power comes from the capacitance also of the transmission lines, and at several places shunt capacitors are connected to supply the reactive power, and sometime SVS, series compensation, sometime some other electronic devices are there to supply the reactive power. So overall reactive power demand should be matched with the supply, and if it is not matched, then the voltage goes down. And normally the both things two things may happen. Two things may happen means sometimes it happens because of the more load. Because of the more load, some area become of low profile voltage. Low profile voltage means at some area, say in the area of Sonipat, the voltage in place of 1 per unit, it may be 0.7 per unit. And so one thing like this, that in certain, and that may sustain also, that you can get the power at that low voltage also. And the other side, it may have that voltage profile may lead the sequence of other events. ये देखिए, voltage profile and one place may lead the sequence of other events, means it may cause the voltage of other area down. One thing, it may cause the frequency affected, frequency goes down, it may affect the power angle, and finally the system may collapse. System may collapse means there will be no synchronization between the rotor and rotating flux. So there will be completely blackout. So two things may happen. One thing may be one complete area may be at low profile voltage. Another thing can be a completely blackout. Both things occur under voltage collapse. Okay. Now we will understand the concept of voltage stability. What actually, let us have, first of all, let us have only reactive power is there, because as we have seen, the reactive power is the main cause of the voltage instability. So let us have this transmission line is purely considered here as inductive, although resistance is there, but resistance of the transmission line is very small. It is a voltage source, some generator is there, and this is a inductive load. Because we are studying the effect of reactive power on voltage, so we consider only the inductive load. When inductive load means current will be 90-degree lagging. Say this is sending end voltage generated here is the sending end voltage available here is the receiving end voltage. Since it is a purely inductive load, so current is 90-degree lagging. Okay, when current is 90-degree lagging, what is the voltage drop here? I into x, J I into x. I into I is 90-degree, so J I x will be means perpendicular to that. So J I x will be this I into x. So you can say this Vs is equal to Vr receiving voltage plus I into x is equal to Vs. So this equation is clear up to here. This is the equation up to this point. This is the equation. Is this equation clear to you? Hello? Tarun Sagwan? Hello? Karthike?
Yes, sir.
Is it clear? This equation is clear?
Yes, sir.
This is a Vs is equal to Vr plus I into x, and I is 90-degree lagging, so Jix will be in this direction simply. So it will be simply Vs is equal to Vr plus Ix. Okay. And what is the receiving end power? This Vr into R. Although Vr into I is the Vi. What is Vi is the apparent power, but since P is not there, P active power is not there because inductance is there, so it is equal to Q. Otherwise, P plus JQ is equal to V into I, but since P is not there, so Q is equal to V. So they are two separate equations. This is another equation. Is this equation clear? Okay. Jagveer, is this equation clear to you?
Yes, sir.
Now putting this value of I, because now why we are doing this? Because now we are going to study the relation or effect of Q on the voltage. Reactive power effects on the voltage. So we are eliminating I, putting the value of I from this equation to here. I is equal to Q by VR. So putting this equation will come. Okay. This equation comes, and this equation, if you this VR in the denominator, taking this denominator on this side, so it is VR Vs VR square. So this equation will be in terms of the quadratic equation like this. This is a quadratic equation. This says the relation, this describes the relation between receiving end voltage and the reactive power. Means how, if the reactive power, reactive power demand is more or less, then how this VR is affected. So this is given by this quadratic equation. So solving this equation, quadratic equation, we can get this VR, value of receiving, what will be the receiving voltage for different value of Q. So solve this, it is a quadratic equation, we can write it minus V plus minus A square minus B square by 4 by 2. It is a minus B plus minus B square minus 4AB divided by 2A. So this, in this way, you can get the VR. It is the equation for receiving end voltage. Sorry, this receiving end voltage. This equation can further be written as VR is equal to this 2. This is the overall 2. So Vs by 2, and this 2 will go inside. So it is, taken here 1 by 2 like this equation. So this equation you see this equation. But if you plot this equation, receiving end voltage, it is formula for receiving end voltage in terms of the Q. If the sending end voltage is fixed, who is maintaining the sending end voltage? By the excitation. Even if with the help of excitation you maintain the sending end voltage constant, even then you see VR receiving end voltage will be affected because of the Q. And if you plot this VR with Q, this equation will come, this diagram, this graph will come. Yeah. As you go on increasing the Q, if you increase the Q, see, if initially if Q is 0, initially if consider say Q is 0 here, so what will be there? If Q is 0, this portion is 0, Vs by 2 plus minus Vs by 2. Then VR is equal to Vs and 0. If Q is 0, there are two values of VR, 0 and Vs. Here at Q is equal to 0, there are two values of receiving end voltage. It is 0 or this. There are two values. If you increase this Q, अगर आप इसे बढ़ाएंगे तो ये वैल्यू कम होगा, ये वैल्यू कम होगा तो ये कम होता जाएगा. ये यहाँ से प्लस दिस इज माइनस दिस, ये कम होता जाएगा दिस. So this will come when Q is the, or you can say 4qx is equal to Vs square, or simply you can say when Q is equal to Vs square by 4x. If you can say if Q is equal to this value, put this Q value here, this will be 0. This will be 0. It means VR receiving voltage will be Vs by 2. ये 0 हो गया तो VR will be equal to Vs by 2. So here you see, if you take more Q, if the demand is more, sending in voltage, this receiving voltage goes down. ये कम होता जा रहा है. Finally, this is the maximum value of the Q. This is the maximum value of the Q you can drop from the system. Here the receiving voltage is the half of the sending end voltage. अगर ये 1 per unit है तो receiving end voltage is the 0.5 per unit of the sending end voltage. तो आपका Q, ये मैक्सिमम वैल्यू ऑफ Q है. इसके बाद क्या है? सिस्टम अनस्टेबल हो रहा है. इट इज नॉट एबल टू सप्लाई टू मेंटेन द कांस्टेंट वोल्टेज. इट गो ऑन डिक्रीजिंग. सिस्टम विल बी अनस्टेबल. वोल्टेज sequence, as I told, sequence of events will take place. Sequence of event will take place means क्या होगा? यहाँ sequence of events will take place. It means it will on even if you decrease the Q. यहाँ देखिए, even if you decrease the Q, voltage goes down. Even if you decrease the Q, यहाँ देखिए, यहाँ अगर Q decrease करेंगे, अगर Q decrease करेंगे तो voltage आपका बढ़ जाएगा. फिर Q decrease करेंगे फिर voltage बढ़ जाएगा. अगर Q decrease का मतलब डिमांड, अगर आपने Q का डिमांड कम किया तो वोल्टेज आपका कंट्रोल हो रहा है. बट यहाँ आप डिमांड कम भी करेंगे तो भी कंट्रोल नहीं हो रहा. वोल्टेज गोज डाउन टू 0. तो पूरा सिस्टम हमारा वोल्टेज कोलैप्स हो गया. 0 वोल्टेज आ गया. यहाँ पे आपका 0 वोल्टेज आ गया. बट so this is the maximum limit of the Q you can draw from the system, and we actually don't allow the system to go up to this voltage V by 2. जैसे 220 वोल्ट है, 110 वोल्ट हम कभी नहीं चाहते हैं. we want to, it can be hardly in distribution side hardly 10% voltage drop, or on the transmission side only 5% voltage drop. 5% means here we can work here only into 5 to 10% range. So Q is not allowed to go beyond this. Q demand is not allowed more than this. So voltage remains in this area. Now, further understanding about the slope means this how the receiving voltage. This is the receiving voltage. How changes with the Q. Q बढ़ाने से Q. This is the slope. What is the slope? Slope means how V changes with the Q. So if we take dVr by dQ here, ये आपका इक्वेशन है, इसको डिफरेंशिएट करो विद रेस्पेक्ट टू क्यू. इसको करेंगे तो टू dVr by dQ, इसको करेंगे dVr by dQ, it will be 1. If you differentiate with respect to Q this equation, you will get this equation. Okay, ये equation आ गई. Okay, so from here we can find the slope. Slope means how VR changes with the Q. So taking this dVr by dQ common, it is 2VR minus Vs, it is minus x. This equation will come. So again this can be written like this. And in the reverse way, dQ by dVr, we can write like this. So from here you see, for maximum reactive power transfer at receiving end, here you see VR, if you put VR is equal to Vs by 2, VR is equal to Vs by 2, this will be 0. This portion will be 0. We cannot take more. This is the critical voltage. Means at this voltage, this dQVR dR will be 0. dQVR will be 0 means system will be unstable. At this point, system will be unstable. So we cannot take the power, reactive power, so that this VR is will be equal to Vs by 2. And how much maximum QR, ये जो हमारा, if you differentiate this QR in this equation, this is the Q. At this Q, system will be unstable. But we want to calculate what is the maximum Q that you can take. Maximum Q you can take from here. You see in this equation again. If you see this equation here, so Q, first of all, write this Q. This Q is equal to, from here, Q is equal to divided by VR square minus Z divided by X. इसको X से divide होगा, means here it will be divided by X. ये इसमें X से divide करेंगे, and then and this VR, this value putting means the this value VR is equal to Vs by 2 here, and putting VR is equal to Vs by 2 here. Vs, this is the maximum value of the Q you can take. QR max will be the, यहाँ x का division और होगा, Vs square by 4x, and Vs square by 4x, and putting the Vs is equal to Vs is equal to 2VR. So this will be like this. Means both will be there. This is the maximum value of the QR, receiving end power. And short circuit reactive power means when VR is equal to 0. In this equation, now you see again, in this equation when VR is equal to 0, putting VR is equal to 0 means it is a short circuit. This, if you short circuit here, if you make the short circuit, how much reactive power will go? इसमें कितना रिएक्टिव पावर होगा? Vs स्क्वायर बाई एक्स. अगर इसे शॉर्ट सर्किट कर दिया तो पूरा का पूरा जो पावर होगी वो Vs स्क्वायर बाई एक्स विल बी द रिएक्टिव पावर. So now you see here, if you from here also this equation here, putting in this VR is equal to 0, you can find Q max, and this Q max will be Q max is the Q short circuit reactive power is the Bs square by X, and you compare this Bs square by X is equal to this. It is the 4 times. This is the 4 times of this. Means when the system is short circuit, then when the system short circuit, it is 4 times of the reactive power that you can take than the maximum reactive power when it is in normal condition. Now, so this is about the how much reactive power you can draw from the system to maintain the system as a stable. Now this is the basic concept we have described about the how reactive power affects the voltage. But in fact, load is not only the reactive power, it is the active power too. Load is the active power plus reactive power, and when load increases, both may increase. Sometimes it may happen only reactive power increase, sometimes it may happen only P is increased, but normally P and Q both are increased. So if the load consists of P also, if the load consists of active power also, then this graph which we have drawn, Q versus Vs, this will be changed when now you see when there is a demand of P and Q both, then here you see S is equal to P plus JQ. You do this analysis. I am leaving it here because our intention is to describe the concept, and finally you will find that this curve, the graph will be like this. If we consider the P effect of P, so the voltage versus P graph will be like this. When P means when 90% 0.5, this is 1 per unit, power factor, when power factor is 1 per unit, power factor is unity, then is the P voltage. When we increase, you see, when the P increases, voltage, जैसे हमने वहां देखा था Q में, when Q increases, voltage decreases. Here also when P increases, voltage decreases. But it depends upon the different power factor. Power factor means different value of Q. When Q is such that it maintains 0.9 power factor, then this is the curve. When it is 0.95 leading, then this is the curve. When it means, what is the meaning of this? If it is a leading power factor means reactive power demand is leading. Leading means it is in place of taking the reactive power, it is supplying the reactive power. So voltage will increase here. It is voltage increase. At unity power factor is this. Now you see this range is very good enough. It is maintaining at 1 per unit. Voltage is being maintained for a larger value of load. 1 per unit voltage is available up to here. You can say up to here the voltage can be within 5% range. Means you can take so much amount of active load, total load. When it is a poor power factor, then suddenly voltage goes very down. Okay, so this is the about relation between P and Q. When load is consisting of P and Q both, then voltage affected like this. And here we have seen the graph between voltage and P. We can also see the graph between voltage and Q in case of a voltage and Q in case of a P. Even P is also present. देखिए पहले हमने जो किया था उसमें P present नहीं था. इसमें now here we are seeing the Q is also present. Voltage versus Q. And this Q is the reactive power injected, not reactive power demand. If you inject reactive power, voltage will increase. If you decrease the reactive power, voltage will decrease. Now we will describe something about the voltage collapse. जैसे हमने अभी आपको देखा voltage collapse के बारे में थोड़ा आपको पता लग गया कि it may happen if the reactive power demand is continuously more than the reactive power supplied. It may happen two things may happen, that sometime voltage profile of some area may be at normal, at very low voltage, some area may be at very low voltage profile, and in other way that sequence of events may happen. Voltage of one area is affected the another area, and the whole system goes the at very low voltage, zero voltage. System will be unstable, or sometime it affects the frequency, and angle instability takes place, and finally system collapse because of the desynchronization. So that now we understand, to understand the voltage collapse, let us again understand the this again. We can see this equation, you see, sending and from above equation just we have described, you see here, from here, from this equation, you see, you note down this equation. This is very starting. Initially we have described about this equation. So note down this equation, and both equation then come to here. This, say, QS sending and reactive power, it is a receiving and reactive power, and I square x. I square x means power consumed in the transmission line. देखिए यहाँ से भी, if you have noted this equation, यहाँ पे भी अगर आपने I से मल्टीप्लाई करें, एक तो यहाँ से भी पता लग रहा है, this QS and QR is QS is equal to QR plus power consumed here. Power consumed here is the I into X or Q, IX here. So sorry, power consumed here is the VR into I. So this power. So the QS QR is equal to VR into I plus QS is equal to QR plus VR into I. This, or from here also. From here also you can say, if you multiply here IS, it is a QS, multiply here I is same, current is same throughout the circuit, multiply I, BS, IS is a QS, it is a QR or I square X. Okay, so it is a I square X. So from here this equation comes. Yeah. QS is equal to QR plus I square X. Is this clear or not? This equation is clear? Hello?
Yes, sir.
Okay. So, and this QS, you know, it is a VS into I, sending end side. And from here, if you put the value of I here, I means here, then you will get I square. I square means QS by VS square. This equation will come. This QS, QR, and VS square by X. This VS square by X we have just studied here. VS square by X we have just studied here. VS square by X. This is the 4 times QR max, maximum power you can take. So from here to this equation comes, and differentiate this equation, because we are trying to find out the reactive power proximity index factor, means कि कितने reactive power पे हमारा system collapse की तरफ जाएगा. So differentiate this with respect to QS. So it will be 1, differentiating this QR by QS, differentiating this with respect to QS, this equation will come. Okay, yeah, इसको differentiate करेंगे तो ये equation आएगा, और यहीं से ये the same equation can be written like this. ये, and again here you see this equation again. This equation again you can write in this form. Yeah, this equation, देखिए इसमें क्या है, QS square 4QR and QS, ये इस equation को दोबारा लिखेंगे तो when you take numerator and denominator on different side, you will get this equation. Means how sending and reactive power depends with the maximum reactive power demanded. Maximum reactive power you can draw, because we are going to find how much sending power we need to supply to maintain the reactive power within this range. So now from here, QS means how much sending power should be there. This equation, if you solve with the help of, because it is a quadratic equation, you will get QS is equal to this. Again, this QS, this equation can be written in this form. Simply 2 taken outside here. Here it is a 16, here it is a 16, here it is a 4. So this 2 will be this, and this 4, and this 16 will nothing, these are the 4. So this 4 taken out, and this equation will come. From here, this again solving this, देखिए इसको now taking QR on one side, here you are taking this QS, QR, this on one side, and differentiate this with respect to QR, this equation will come. This equation will come. And finally you see, finally from here, solving this equation, you get this. This is called voltage collapse proximity indicator factor. इससे क्या निकल के आ रहा है? If you study this, that if reactive power demand is equal to the maximum reactive power, जितना डिमांड है हमारा रिसीविंग एंड रिएक्टिव पावर वो मैक्सिमम के बराबर है, तो 1 - 1 is 0 and it is infinite. वोल्टेज कोलैप्स प्रॉक्सिमिटी इंडिकेटर फैक्टर मतलब हमारा वोल्टेज मैक्सिमम की तरफ अगर डिमांड है तो हमारा ये क्या हो रहा है, हमारा सिस्टम कोलैप्स की तरफ कोलैप्स हो गया. एंड इफ QR is 0, if QR is 0, then voltage collapse proximity indicator factor is 1, means system will not collapse. If there is no QR, voltage will not collapse. Now it means depending upon the value of this VCPI, voltage collapse proximity factor, इसकी वैल्यू 1 से जितनी ज्यादा होती जाएगी, if it is a 1, then system is stable. 1 से जितनी ज्यादा होती जाएगी, 2, 3, 4, 5, 10 infinite, उतना ही हमारा सिस्टम कोलैप्स की तरफ बढ़ता जाएगा. So this is about the various factors leading to the voltage collapse. You know what are the factors? It is because of the reactive power. Reactive power is inadequate to supply, and this reactive power comes not only the excitation system, it may comes, as I told in the beginning, from the SVS. It may comes from the load of the SVS. It may come from the it may be controlled with the help of the tape changing transformer. It comes from the transformer, it comes from the condenser, it comes from the synchronous compensators and switching capacitors. So with the help of this, we try to maintain the reactive power, try to control the reactive power. And we have seen near the maximum load, when the load is near to QR max, sending end voltage of the reactive power required is extremely very large. तो हमें बहुत ज़्यादा, अगर अपना रिएक्टिव पावर इतना है तो सेंडिंग एंड रिएक्टिव पावर बहुत ज़्यादा चाहिए. उस समय हमारा VCPI बहुत ज़्यादा हाई होगा और सिस्टम कोलैप्स हो जाएगा. तो दिस इज अबाउट द वोल्टेज कोलैप्स. इज देयर एनी क्वेश्चन अप टू नाउ? And these are the methods to control the voltage. Now you see here, now the detailed study is there, how to control the voltage, and various methods are, you see here, various methods are like this: shunt compensation, series compensation, excitation control, tape changing transformer, booster transformer, induction regulators. With the help of these, we control the voltage of buses. And then detail of each, कितना कंपनसेशन होना चाहिए, जैसे कैपेसिटर लगाना है, शंट कंपनसेशन है तो कैपेसिटर लगाना है, तो कितना कैपेसिटर लगाना है, कितना रिएक्टिव पावर होगा, कितना कैपेसिटर लगाना, दिस इज द फॉर्मूला. दिस कितना वोल्टेज करना है, कितना रिएक्टिव पावर, दिस इज द फॉर्मूला. यू सी वोल्टेज कंट्रोल करने के लिए कितना रिएक्टिव पावर चाहिए, कितना वोल्टेज है. सो द वेरियस स्टडीज आर देयर, बट as per the syllabus, voltage stability is over. This unit is complete. If you have any question throughout this complete unit, we describe the angle stability. We describe the load frequency control, primary and secondary ALFC, Then we describe the voltage stability, we describe the excitation of this unit. So if you have any question throughout or from any of the topic of the unit, you can also discuss.